All right, so getting in. Put it down. Still echoing. Okay. I'm going to try to put it. Is that better? No. Any better? No. How about if I just hold it? Is it better? Is that better? Still. I can just speak loud. Okay. Can I talk loud? Okay. Back here? No? Better? Worse? No? Better? 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 That's a little better, maybe. No. Better over here? No. Why am I the only one who has this problem? All right. All right. Right in the middle, right in front of my slides. Okay, maybe is that? Yeah. Well, I can certainly speak loudly without the mic. I guess the problem is the recording. I'm going to hold it down here. Is that okay? And then a little better. So this is some work that I've been doing with some of my undergraduate students who are highlighted in white here, along with the Candles team. And I'm going to start with an apology for those of you that were at the Candles meeting. You're welcome to tune me out, and I will not be offended. My talk today is on quiescent galaxies, and in particular, the fact that we find a lot of disk-dominated quiescent galaxies. And this work that I've been doing has really been motivated by some work that I did now 10 years ago, where we were looking at quiescent galaxies before we had this term quiescent galaxies, actually. We were looking for the oldest massive population. And we were really just interested in trying to figure out what the formation was for these galaxies. And no one had really looked at the structure of these galaxies before. They had looked at the stellar populations, but this study that I'm showing you here from my 2007 and 2008 papers was really the first detailed morphological study of these massive potential galaxies. And one of the interesting things that we discovered in this paper is that some of these galaxies are nearly pure exponential disks. So this is an example. We had imaging in ACS and in McGrath. This was before the days of UC-3. And our best fit model, you can see we tried to fit it with a number of different types of models. And the best fit one is a nearly pure exponential profile with a very small stellar nucleus, or equivalently a specific index of about 1.5. So I should say I will disagree with Mark slightly, because we do have some examples of nearly pure exponential disks that are quiescent, and I think you'll agree with me that this looks very quiescent. All right, so that was the early research, and we also had a paper at higher redshift, and we found some more examples of these at slightly higher redshift. So we only had a handful of galaxies back then to look at, so we didn't have anything to make statistics with. Now, thanks to Candles, we can do this on a much larger sample. And so throughout the talk, when I say massive, I'm referring to the galaxies that are greater than 10 to the 10th solar masses in stars. And when I say they're quiescent, they've been selected via the DBJ diagram. And when I say that they're disks, I'm saying that either their bulge to total fraction is less than 1/2, or if they're not well fit by a two-component profile, if we only need a single component to fit them, then we'll use this Sursig index less than 2.5. We're looking at a redshift range between 1/2 and 2.5. To do this bulge to disk decomposition, and with candles we have that. So in the past, people have referred to this dividing line between Sursig index 2.5, things less than 2.5, we've called disk-like, and things greater than 2.5 we've called spheroidal. But I would argue now that we have the mechanism to go beyond single Sursig fits and actually do a bulge to disk decomposition. So that's what we have done, and so I'll just show you our examples, a couple examples here. So these are 3 massive quiescent galaxies that we selected from the Kendall's field. And if we fit these with a single Sursig component, these are the residuals we get. And so you can see sort of by eye that this galaxy looks. There's a clear disk component there. There's also a clear spheroid in the center. Here again, we see some disk component, but the spheroid component looks like it dominates a little bit more. Here, it looks like we have a pure spheroid. So when we do the single component fit, sometimes we get the right answer and sometimes we don't. So down here, for instance, we get an N-4 local Earth profile, so I would agree with that. Here, we have a sort of an uncertain Sursig index around that 2.5 dividing line. It's hard to say whether it's disk or spheroid dominated from a Sursig index here, even though by eye we can say that that's spheroid dominated. And then here I would say we get the wrong answer. Our single Sursig fit here is giving us a very high Sursig index when quite clearly there's a significant disk component here. So when we do this with 2 components, now you can see our residuals, how they change, and in fact they get much better for these top 2 cases. Here the residuals are pretty much consistent between these 2, and we also get pretty much the same answer regardless of whether we're using single component or 2 component for this particular galaxy. For these other ones, I would say here we get a bulge to total about 1/3. That agrees more with what we see by eye. Here we get a higher bulge to total ratio, agrees with our spheroid dominated. So we've gone in and done this 2-component fitted for all quiescent galaxies in the Kendall's fields. And we're determining whether they're disks or spheroids based on either this bulge to total fit if 2 components are required, or the single Sursig index if we don't need a second component. So for instance here, our residuals didn't change very much, so we might as well stick with just a single component. So how do we determine whether we need 2 components or not? Just very quickly, we use this residual flux fraction in order to determine that. And so basically, by looking at how many residuals are left over after you subtract off your best fit model, if that changes significantly from 1 component to 2 components, then we will use 2 components to fit the galaxy. If the residuals don't change all that much, then we will stick with the single component so that we're not overfitting the data. So how well can we actually recover the real bulge to total fractions in galaxies? So in order to get at this question, we simulated some fake galaxies, basically chose a parameter space that agrees with the observed parameter space of galaxies, so different bulge and disk radii, different axis ratios, different Sursig indices for the bulge. And threw in the candles PSF and added noise to replicate candles like images, pixelated them to the candle scale, and then we put them back into GalFit, fit them, and see what we recover. And so this is our recovered bulge to total minus the input, the true bulge to total that we started with in our simulations. And of course, if we have 0, then we have a perfect recovery. You can see there's some bias to this recovery, which, as Sandy pointed out, we can correct for. But in general, we do a pretty decent job recovering the proper morphology of the galaxy, recovering whether it's a disk or a sphere. All right, so when we do that, this is a sample of the galaxies that we get in candles. So you can see, this is our low redshift sample. So you can see quite clearly several of these are very obviously disks. We have some face on disks, we have some edge on disks. And as we go out to higher redshift, you can see that the disks get smaller. So here's our high redshift sample. Again, you can see still clearly that there are significant disks in so many of these galaxies, but the disks are getting smaller. All right, so you might say, looking at these, are you worried for these things that look like they're nearly edge on? Are you worried that they're red just because of dust rather than the fact that they're really quiescent? And so we looked at where they live in UVJ space. And you might expect that if they are sort of reddened due to dust, they might live closer to that dividing line in UVJ space. But in fact, we don't find that to be the case at all. So here, in 4 different redshift ranges, I've plotted where the quiescent spheroids live and where the quiescent disks live in this space. And you can see that they basically occupy the same region of UVJ space. There's no preferred orientation for disks to be sort of closer to this dividing line or anything. All right, so with all of these 750 plus galaxies, we can do some statistics. We can look at the evolution in redshift of quiescent galaxies and how many of them have disk components. So if we do that, the fraction of all quiescent galaxies as a function of redshift, at very high redshift, you have upwards of 35% of the galaxies are disk dominated. So not just that they have disks, but the disk is the most significant part of component of the light. And as we get to lower redshifts, then the number of these disk-dominated systems declines, presumably because they're either building up their bulges and they're becoming more bulgy, less disky, or because they're merging and becoming spheroids. All right, so and then here's just a plot to show what we saw by eye, that these disks, like their spheroids, tend to be more compact than star-forming disks at the same epoch, at the same mass range. All right. So the importance of quiescent disks. So what I would like the takeaway point here to be is that we have some galaxies that are still disks. They seem to have quenched before they've transformed into spheroids. And they also tend to be more compact, so it's possible that they have to have undergone some kind of compaction event because they're not these extended star-forming disks. So the question is how, first question is how do you form these things? How do you assemble this much mass into a disk at early times? And our original picture of galaxy mergers, while it can work, you require really gas-rich progenitors, and you need some very specific initial conditions in order to get this disk. So an alternate mechanism here would be this idea of cold modification, which is very efficient for forming compact objects and also building up angular rotation. So once you form the disk, then you also have to figure out how to shut down the star formation. I think this is maybe the bigger problem, is how do you shut down the star formation. So AGN is one possibility. AGN, we would expect AGN to be growing in the centers of bulge-dominated systems, but this probably is a problem here, right? Because I mentioned that some of these are merely pure exponential disks. So I'm not sure whether you can do this entirely with AGN feedback. So an alternate mechanism may be some sort of environmental halo bridging. And so this is what we've been looking into recently. So I'm only going to show a few results from this. But we've been trying to get at the environments of these galaxies, trying to understand more about the environments of these galaxies. And environments are hard to do, especially for passive galaxies, because we're reliant on photometric redshifts. But what we've done is we've taken each one of our quiescent galaxies, we've drawn an aperture around it, so 100 kiloparsecs there. And so we're looking at all the projected galaxies that fall within this 100 kiloparsec region, and then look at the redshift distribution of every galaxy that falls within this aperture. If this galaxy is in an overdense environment, we would expect there to be an excess of galaxies of the same redshift within this aperture. So here is our sort of cumulative histogram for 4 different types of galaxies. So our quiescent galaxies are on the top, so quiescent spheroids and quiescent disks. And then on the bottom, we have our star-forming galaxies, star-forming spheroids, and star-forming disks. And we have the same number of galaxies in each one of those bins. So we've mass matched them, we've matched them to the same redshift, and we've picked the exact same number for each plot that we're showing here. And so you can see the sort of underlying galaxy population is similar for all these, as you would expect. That's just your background population. And then what's different is the sort of strength of this spike here at delta Z of 0. So the strength of the spike tells you about how strongly clustered these different populations are. And you can see there's a spike at each one of these because massive galaxies in general like to be clustered. But the spike is much stronger for our quiescent spheroids and our quiescent disks. It may be a little hard to see. The quiescent spheroids actually are slightly higher than the quiescent disks here. It looks like within the areas here, I mean, there's more than 500 galaxies in that spike. The quiescent disks may be in a slightly less dense environment. Maybe the disks are sitting on the edges of the overdensity, so when you do this aperture, then you're getting a lot of galaxies that are not nearby, whereas for the spheroids, they're sitting more towards the centers of the overdensities. That's one idea. So we did try to look at this more with some data from Masadi et al. From their recent paper on environments, on overdensities in Candle's fields. Red regions here are higher overdensities, and blue regions are underdensities. So I should say that they did this using mostly spectroscopic redshift, and so it's really hard, again, to use this data for passive galaxies where you have large photometric errors. But you can see that the disks, which are overplotted here as pluses, tend to live near these red regions. They tend to avoid the blue regions, but not in all cases. Here's one that's sort of overlapping on a blue region. So this is still a question of whether environment is really playing a role, or whether environment maybe is a red herring. We're not sure yet. So this is something that needs to be solved, but it may be hard to solve until we get to the era of JWST. All right. So halo environmental question, maybe there's some hints that these quiescent disks do live in more dense environments. There may be other processes such as morphological quenching, growing a bulge and the bulge stabilizing the disk, but this process may take too long to actually produce these types of systems at redshift 2. All right, so I think what's interesting about these systems is that they are very similar in terms of bulge to total ratios and masses of local S0 galaxies, but they're much more compact. So there may be some period of sort of inside-out growth by dry mergers that would help to increase the size of these and grow them into our classic S0s that we see today. And so understanding the formation of these types of things may lead to an important understanding about this sort of mystery we've always had about how S0s form. All right, so I'll just end with my summary, which is that massive quiescent disks are common at high redshift, up to 30% of the entire quiescent galaxy population. We need to understand how they're formed. I think a good way to form them is through this cold gas accretion, followed by some compaction event. And then finally, we need a mechanism to shut down the star formation in these galaxies, which I think is really complicated. Possibly AGN feedback, but for the less bulge-dominated systems, it's not clear to me that could work. Possibly halo quenching, but again, it's not clear to me that the environments are actually quenching these things, and rather that it's their own environments that are quenching other galaxies. Morphological quenching timescales may take too long. So this is an open question, I think. And then finally, at later times, since we do see the fraction of disk-dominated quiescent galaxies falling off as we get towards the local universe, mergers are probably important later in both puffing up these galaxies to increase their sizes, as well as to convert some of them from disks into spheroids. Thank you. So part of how to reconcile that, I'll take a stab at it and then I'll let you. Part of how to reconcile that, I think, is that there are certainly galaxies in my sample that have bulges, which I think you agree with. There are certainly galaxies that are disk-dominated that have significant bulges. I'll let you say something too. So if I could modify your statement that there are no bulgeless disks, there are very few.
No, it's not just that if you take it below 0.2, you see that everything is start falling with the huge the difference between Quiescent and the start falling. While you go above 0.2, the difference is much larger in the other thing. You have very, very few masses of difference in the definition of this. No, the theory is the same definition. The other thing, very, very piece of the I think we have a
well, just on this issue, you showed that there's that spike a little bit higher in the quenched spheroids than the quenched spheroids. And that's presumably the high density region. So is there some difference in the low exposure ratio or other properties for the ones that are in that region compared to the ones that aren't? For example, is it an environment that's causing quenching without the presence of bulge or mass?
That's a good question. That's something that we can look at. When we start breaking it down into bulge to total ratios, our number of statistics fall. So it might be a little murky, but definitely something to look at. Yeah. Right. Yeah.
And also
Yeah. So what I'm saying is that these quiescent disks are much smaller than the star-forming disks at the same mass. So you're saying they form small. This is the progenitor bias. Yeah. So right. So that's absolutely possible. Yeah. Okay.